Well, howdy. Welcome back to the SOFO sessions. This is session 8. It's the transfer function part of the sessions. This is part 3, fun with phase response. I get the feeling like this is the main event. I think people have been waiting for this one. I hate to tell you this, though, that this is going to be 2 parts just to get through phase. Normally, when we present this in class, I normally cover it in about 4 hours. 3 hours, try and go at a gentle pace. There are other friends, instructors out there that spend an entire day or multiple days on it. Here we're just trying to get some of the basic concepts down. In this session, we're going to talk about why are we measuring phase response, what are we using it for. We're going to talk about reading the phase trace. Today we're going to spend mostly focusing on measuring time offset in the phase trace, measuring latency or delay through a system. Next session, we're going to get into more complex phase responses, phase shift, and we're talking about measuring polarity as well. We'll see a little indication of it in today's, but mostly that's going to be in session 2. So yes, when you start asking questions about stuff that's going to be covered in the second half of the session, we are going to put you on hold and say, come on back. So we're going to talk about minimum phase and no free lunch, just basically this idea that given a magnitude response, you create a magnitude response, you're going to necessarily have a certain amount of phase shift that goes along with this. You can't do the magnitude, change the magnitude response without having the phase shift impact. We're going to be talking about our TF, the time reference. Basically, what is time zero? This concept, when we were doing magnitude response, our level reference was the level of the reference signal. In fact, for the phase measurements, for the phase response, it's the time, it's the arrival of the reference signal. So we'll dig into that. And we're going to be about reading the time offset. It's all about the slope of the trace. That's one of those things that people, some people get right away. Some people, it's not as obvious. They want to see a number. They want to see the numbers on the edge of the phase plot. That's not where it's at. Quite honestly, I can condense this whole class into about 15 seconds worth of just saying leading, lagging, on time, slope. If you walk away with anything here, that information is going to be the most important thing. So I'll highlight it. I'll point it out. I want to make a couple points here. Our treatment of this is I'm not really doing a mathematically rigorous, in-depth treatment of this subject. We're not expecting anybody to be engineers. I'm not going to get too particular about terminology. I like to use clean terminology, but I'm not a big fan of people being overly picky. We want to talk about concepts. I mean, when I say to somebody, "Hey, hand me the phase reverser," and of course somebody goes, "Oh, it's polarity reverser," I'm like, you knew what I wanted. Just hand me that barrel, right? So let's talk about the basic concepts. We'll try and keep our language clean. But there's a place in here where we're going to talk about leading and lagging energy. Energy, we're talking about the relative arrival time of 2 signals, the output of the system, the measurement signal, and the reference signal. So in our measurement, we're comparing the arrival of the reference signal to the measurement signal. Now, one of the first steps we take in our measurement is to delay our reference signal to be in time with the measurement signal. And we're going to talk about leading and lagging. Now, leading and lagging, what we mean by that is energy either coming before the arrival of the reference signal or after. Lagging is arriving after. Now, those 2 terms do have a rigorous definition when you're talking about phase response, and they kind of mean the exact opposite when they talk about leading phase and lagging phase. Just keep in mind, when I'm using those terms throughout this presentation, what I'm talking about is the energy in one signal arriving ahead of or behind the energy in another signal. So let's get started. We're going to kick this off. Of course, my name is Jamie. I'm the director of training here. I think it's really funny that in some old videos about 10 years ago, I used to introduce myself as like the the second line cook in the third shift, or I'd give myself all sorts of weird titles. And somebody actually got really pissed that they had gone to a video about FFTs, and they were really pissed that it was being given by a line chef. So I don't joke like that anymore, I guess. But you got Chris. Chris is online. He'll be doing Friday's session. We got Michael riding shotgun here. And, of course, Gavin is out there helping wrangle the whole thing. And, of course, Rational Acoustics. Support at Rational Acoustics. That's your go-to address for asking questions. Training and sales also are good places to get in contact with us. There's our phone number. We're located in the northeast corner of Connecticut, but you can't stop by because we're distancing right now. But let's get this started. So again, we have our friend Jean-Baptiste Joseph Fourier. What Fourier, basis of Fourier analysis is, he's saying that all of our signals, we're sound engineers, so we're working in audio, we're working in sound. There's our sound wave, amplitude versus time. And what he stated was that basically that complex wave that we're working in is basically made up of a whole bunch of simple sine waves. So, system engineering, what a lot of us that are involved in, we're using we're basically adding a signal back to itself. So we have the high driver and the low driver trying to combine to form one speaker. I've got two speakers in an array trying to combine to be one speaker. I've got direct energy, reflected energy. It's just adding a signal back to itself over and over again. So the cool thing about this is it simplifies quite nicely that signal addition is basically sine wave addition. So what we want to pay attention to is just our basic building block, our friend, the sine wave. So there's a couple things that describe the sine wave. Okay, one, it's an oscillation. It's just a repeating function. So it's an oscillation in pressure that then we convert to an oscillation in voltage, and then we digitize it and have an oscillation in level. But basically, it's just a repeating function. So the first piece of information we want to know is how long does it take to go a full cycle? That's the period of the wave. 1 over the period is the frequency. The second thing we're asking about it is then how big is the oscillation? How big is that wave? So that's the question. How loud is it? So that's the magnitude. That's the amplitude, or how loud it is. So what frequency, how loud it is. And then the last piece of information we're asking about here, and this is all about today, is the phase. Where are we in the oscillation? So I'm going to look at the 1K on input of the system, the 1K on output, and I'm going to say, okay, we've matched. We got the same period, we're same frequency. So, okay, how loud are you going in? How loud are you coming out? That's going to give us the magnitude response. And then we're going to say, where are you in the oscillation? Are you at 0 but heading positive? Am I at full positive? We call that 90 degrees through the oscillation. If we're back at 0 but we're heading negative, that's 180 degrees. If we're at full negative, we're at 270, and then we come around to 360 degrees. Now keep in mind that 360 degrees, we're back where we started. There's only 360 degrees of phase. Basically, we're going to get a number when we ask the 1K on input and the 1K on output. We're going to get a number about where we are in that oscillation within 360 degrees, basically. Okay, so why are we measuring the phase response, and what are we measuring? Okay, so we can break this down into two basic reasons why we're measuring it. We're measuring the phase response of a system because we want to know the time response of the system, how it's treating its signals in time. So we're trying to figure how long does it take for the signal to get through the system. When I start trying to time different elements in the system, I'm trying to get them to probably be arriving at the same time at a given place. Or I want to make sure that one system's energy is arriving before another system's energy because I might be trying to move my imaging around or something like that. But basically we want to know how much time or delay is there through the system. And then we also want to know how is that signal affected in time. So how is it smeared out in time? What we're going to find out very quickly is that when I send my signal into the system, not all the signals get out at the same time. Basically, whenever we filter the signal, we're going to smear it in time. So we're going to dig into that a little bit. That's that whole minimum phase type of thing coming in. So the first question we're going to be asking is, what is the time response of the system? The second question we're going to ask is much more of the system engineering thing. We want to determine relative phase. So I've got two signals, I've got two arrivals of a signal, and so I'm trying to figure out the relative phase between them. So I want to predict or maybe adjust the systems to get a certain interaction between the systems. Normally we want stuff to add, but if we're trying to create cancellations like with a cardioid subarray, we're actually trying to create the interaction where they're subtracting from each other. And here we want to also be able to choose polarity. So polarity comes down when we're talking about wiring an electrical system. We've got a positive and negative, so we have a unique opportunity to mess that up. Now sometimes we want to mess it up for a reason, but oftentimes it's a problem. And what we want to do, if I'm just using one system, right? If I'm just using one channel, what sounds better, a pin 2 hot amp or a pin 3 hot amp? And please don't argue an answer there. They sound the same. The thing is that, I wonder if that's blowing up online. Ignore that question. Run away from those people. Okay, but the thing is that as soon as I have two radiating sources, then I need to choose the polarity of one system that best behaves with the other system. They make them best get along with each other. So that's one of the reasons why we're taking our measurement. So in one case, we're just saying, what is the response of this? And then what is its response relative? So those are our two standard engineering questions. So when I'm measuring a system, I put a signal in, signal out. There's our classic system model. The phase response is going to give us three different pieces of information. One of them is just going to be, what is the overall delay through the system? It's all the energy taking a certain amount of time to get through the whole system. The second question we're asking is, was the energy smeared out in time at all, right? Was the system due to filtering? Did some frequencies get out before other frequencies get out? So what is the time response of the system? And then the last piece of information that we're looking for is polarity. Now here's the thing. Polarity is going to show up differently than phase shift. So we're going to dig into that. Polarity mostly we're going to be talking about in the next episode. But one of the things is that we're going to do is, let's say I have a main system and a fill system. So when I bring in that fill system, let's say it's not even the same manufacturer, and it's a box you found in the back room, so you're plugging it in to be a fill to cover some area. You need to choose the polarity that you're driving that to make it work with the other system. Well, I'll tell you how to do it. I don't expect it to make sense. But the first thing is that you're going to time to the same frequencies in the same box. So when we take our measurement, we're going to take the time offset out. We're going to time to the same frequencies in the same box. Then we're going to look at the phase response of that system. And generally, we don't have the ability, although it's more and more we're getting the ability to change the phase response of the system. We've got all these cool all-pass filters but let's assume that you can't change the phase response of the system, so you're going to choose the polarity that's going to make this box with this phase response and that box with that phase response, what's going to make them behave best together. It's just managing compromises, but that's something that we have to do. Okay, so minimum phase is just the concept that as soon as I filter a system, I'm going to have a time impact there. Why? Why does filtering cause? Well, you think about it. Filtering treats one frequency or one set of frequencies different than another frequency. Well, what's the difference between frequencies? Well, it's their rate of oscillation. So the mechanism that the reason why you have a time impact there is you can't do that in zero time. Right? The mechanism has to differentiate based on rate of oscillation. A high frequency oscillation is going to oscillate very quickly. A low frequency oscillation is going to oscillate slowly. So that mechanism will necessarily have a time impact. So we're actually working a three-dimensional puzzle. A lot of people simplify it to just magnitude versus frequency, but we're going to find out that phase is an incredibly important part, and the time response is an incredibly important part of the puzzle. So that's where we get the no free lunch, is that what we're going to find is as we get more and more severe in magnitude response, as we start doing higher and higher order filters, we're going to get more and more phase shift, and we're going to pay for that. Okay, so the big question really when we're adding stuff together though, and we'll just simplify it to one frequency. So I'm adding two sine waves of the same frequency, same level. What do I get? Well, the answer is it depends, right? The phase is going to determine the outcome, right? So that's going to tell you something, that if we're adding signals together, that's our whole job as system engineers. And I can't tell you how they're going to interact until I know the relative phase between them. Kind of tells you it's an important element in the whole equation here. Now, the thing about this is also pointing out one of the keys here, because when the two systems are equal level, this is one of the system engineering keys, but systems interact most where they're equal level. That's the thing when we work as system engineers, we are trying to minimize equal level overlaps, right? Because there you get the most audible interaction. And where we do have equal level, let's say the crossover between a low driver and a high driver, we want to manage the relative phase at crossover because that's where they're equal level. And so that's where you can get the full addition, or you could get no addition, no subtraction, or in the worst case, if they're equal level and 180 degrees out from each other, that's where we get complete cancellation. So if we look at this, here's the same thing, but in the top plot, you've got the dark black line is the summation, then you've got a dotted line and a solid line. Well, in the top plot, the top graph, there's 0 degrees of phase difference between them, so they both add up really nicely. You get a double, you get full addition, fantastic. Now, as one is arriving later, is shifted, so there I've got 90 degrees shifted, I see that I get addition when I add those two guys together. I just don't get complete addition. It's when we get to 120 degrees shifted, that's where we get no addition, no subtraction. So we get the same level out as we had before. When we get past 120 degrees, this is where we get into cancellation, with the worst case being 180 degrees. Now, one of the things I want to point out here is that the horizontal axis here, the x-axis here, is time, right? And so it's in quarter periods is what's kind of marked out here. But basically, phase shift connotes some amount of time. So phase shift is a sort of a time mechanism. But the one where I've got 180 degrees of phase difference, I can actually get 180 degrees of phase difference without shifting in time. I can get that by an electrical system just swapping positive for negative. And this is where I get my worst case, because now I have 180 degrees difference and I'm getting that at all frequencies. And so this is where I can get some really bad or potentially useful things happening depending on how we use this. But basically the thing that we want to remember is that a polarity inversion is swapping positive for negative electrically. It doesn't have a time component, whereas phase shift is time. And so we're going to be able to root the difference between the two out because polarity is not going to show up the same way as a shift in time will. Okay, so reading the time offset and the phase response is all about our time reference, right? So what we're reading here is we're comparing the reference signal to the measurement signal. And we're saying, okay, how far apart are they in phase? That's the number that we're going to be coming up with. Now, let's say I have a system, I'm measuring a system, and that system has 1 millisecond of delay going through it. So it's just this black box. The black box has 1 millisecond of delay in it, input relative to output. Right? So the question is, how much phase shift does 1 millisecond of delay equal? And the answer is, it depends. Our favorite answer. I think that's Snodcon's motto, and it's very wise. And so what we've got here, let's look at period versus frequency first. This is something that's probably, you guys are probably aware of this, but as the period gets larger, the frequency gets lower. So a 1 millisecond period gives me a 1 kilohertz wave, a 2 millisecond period gives me 500 cycles, 500 hertz. So, okay, hopefully nobody's surprised here. So let's say we have our system here, and our system has 1 millisecond of delay. That's indicated by the yellow gap here. And so you've got the reference signal, then the measurement signal is starting 1 millisecond later. Well, at 250 cycles, 1 millisecond of delay equals 90 degrees of phase shift. At 333, it's 120. At 500 cycles, it's the dreaded 180. By the time you get around to 1K, you're back to 0 degrees phase difference, and by the time you get around to 720, you're back to 0 again. We're going to take a look in the next episode. We're going to be looking at the mechanics of a comb filter, and this is going to play directly in it, where the comb filter frequency is going to be 1 over the time offset. So if the time offset was 1 millisecond, 1 over 1 millisecond is 1 kilohertz, so we'd see addition every time it comes back around to 360, and we'd see cancellation halfway in between. So we'd see addition at 1K, 2K, 3K, 4K, and a subtraction at 500, 1K5, 2K5. We'll get into that. A lot of you guys have seen this before. So we're going to graph this information. We're going to throw it up in a nice flat plot. Now, the thing we want to be aware of here, though, is that phase is basically continuous. So 0 degrees and 360 degrees are the same place. 90 degrees and negative 270 are the same place. 180 degrees and negative 180 degrees are the same place. So even though we're doing this nice flat graph, this nice XY graph, the thing we have to keep in mind is that what we're actually going to be doing is we're just breaking apart. Something just happened. So what we're doing is we're breaking apart this circle and we're flattening out for you. So at the bottom of the screen is 180. At the bottom of the screen is negative 180. Keep in mind that the top of the screen and the bottom of the screen are actually the same place. So if I had a line going off this plot, it's going to show up back around. Now there's some really cool graphics out there that you guys may have seen of just, the phase wheel and showing phase wrapping around. There's all sorts of ways of describing this. But the thing to be aware of with our phase plot is that it's a continuous plot. So the top of the screen and the bottom of the screen are linked. So if we were to graph that information that we just had, right? So we had 90 degrees at 250, 180 at 500, 333 at 120. So if we were to graph this, what we would see here is we'd see at 250, we're at 90 degrees, at 500 cycles, we're at 180. And then it continues along till we're back at 0 again at 1K. So we're just graphing that same information. This is what 1 millisecond of time offset looks like on a phase plot. Now, here's the thing. This little guy right here, we call it a rack. This is a graphing error. This is a graphing engine not knowing that this guy and this guy don't connect by going through the plot. Now, some people say that this is a useful piece of information. I find it distortion because the thing that's really important in the phase graph is the slope or the trend of the graph. And this is not real data. This is fake data. And so this guy, this guy, that's fake data. That's real data. That's fake data. That's real data. That's fake data. So we haven't graphed the phase trace, the racks in the phase trace for about 14 years. But I figured I'd show it to you because if you're looking at some systems, they don't take the time to clear out the fake data. Anyway, so what we see here is we see the racks taken away, and so we see the line going off the top and continuing on the bottom. We're going to store that in our minds for a second because we'll see how that plays out in our phase trace. There's some cool stuff about it. Okay, so the phase response shows the arrival of the measurement signal relative to the reference signal. So, okay, the first question's got to be, okay, so what time is the reference signal arriving? Right? So our whole basic model is we're going to grab the signal before it goes into the system. Then we're going to set a delay in order to time the reference signal. So it's going to take some amount of time for the signal to go through the system. So we're going to delay the reference signal to be in time with the measurement signal. So effectively for our measurement is going to be time 0 plus or 0 plus whatever the delay is set to. So we can say, hey, the reference signal is arriving at 42.13 milliseconds. So now the phase trace is going to tell us about the arrival of the measurement signal relative to that 42.13 milliseconds, right? So what is T0 for our measurement? All right, so T0 is the moment we grab that signal. So if we're using, for the measurement we're going to be doing in just a second, we're going to be using the output of the console. So that's my T0 right there. Let me give you a really stupid example. Let's go to Sweet Baby James. James Taylor recorded that album 50 years ago or so. Okay, so he goes out there. He's in the recording studio. He's playing his guitar. I believe it was recorded onto wax cylinder, and then it got onto vinyl, and then into mini disc or whatever, and then it got digitized or it got digitized to get on mini disc. You got me there. But basically, it ends up on iTunes, buys it, and then I put it on my phone, and I have it in my iTunes there, and I play it. So basically, I play that through the system. Well, from the time that the signal was created till it showed up at that point, that's like 50 years worth of delay. Guess what? I can't tell you anything about that delay. All I can tell you is from the moment I grab that signal, I can tell you how long it takes to get further down the path. So what that means is that if we want to measure latency, what we want to do is we want to grab the signal before it goes through the system. So if I wanted to measure the mixer, let's say I wanted to know about latency on insert paths or whatever. If I wanted to measure the latency through the console, what I'm going to do is I'm going to grab the signal before it went into the console and then compare it to the signal coming out, and I could tell you how long it took to go through that system. So our time zero for our measurement is going to be that moment we grab the reference signal, and then of course plus whatever your measurement delay is set to. Okay, so the key to this is the thing that I want you to take away. If nothing else, the next 3 slides are the whole shooting match here. Okay, so the information you're looking for timing is in the slope, the rate of change of the phase trace. So if the phase trace is trending downward from left to right, what that means is the energy of the measurement signal is lagging behind the reference signal. You can see that in the live IR here too. In the live IR measurement, the center of the screen represents the arrival of the reference signal. You'll notice that whatever delay time you're using for the reference signal is going to show up right here in the center. And so what you're going to see is, in this case, the measurement signal's energy is arriving after. Then we've got, when they're on time, the slope of the phase trace is going to be horizontal. It's going to be 0 slope. And then when measurement signal is arriving before the reference signal, we're going to get an upward. So that's our leading case. Now here, this is illegal. This is what's known as a non-causal system, because what this is representing is the measurement signal is arriving before the reference signal. The output of the system is arriving before the input of the system. Now, if you have a system like that, then you need to head out to Macau or Vegas or someplace like that, because you can make a ton of money. Or you could just go to the stock exchange. Any of these things, if you have a non-causal system, I'm not sure what you're doing in audio. Okay, but here's the thing. In our measurement, it's very possible for us to have a situation where I've got the reference signal lagging behind the measurement signal, or what we'd say is the measurement signal leading the reference signal. Right? That, imagine if I placed a microphone out in the room and I set my measurement delay, and then I took that microphone position, I moved it closer to the speaker. Now the latency through the system is shortened up, right? There's less travel through air. And so if I don't reset my delay, now I've got a situation where the measurement signal is effectively leading in our measurement. So the thing that you want to take away here is just this: lagging, on time, leading. If you got that, you can walk away, declare victory, go get a beer. Okay, so I'll go back. That's what is T0. Okay, so I don't think this is helpful, but I think it's kind of funny. When you become more of a ninja in this, you start to be able to look at the slope of the phase trace and calculate the amount of delay you're looking at from it. So basically, the change in phase over the change in frequency represents an offset. So that slope of the phase trace actually represents a time offset. Yeah, what? I don't. Oh, here, I'll show you the math. You don't have to do this. But basically, what you're looking at is the change in phase over a given change in frequency. And then what you're going to do is we're going to normalize that change in phase to say, okay, one cycle, so how many cycles does that represent? Normally it's a fraction of cycles. Or sometimes what you'll do is you look for where it's crossing zero here and figure out how many hertz is it apart, what's the bandwidth between one zero crossing and another zero crossing. But so basically you say, okay, it's changing this many degrees phase in this much frequency. How long would it take to do one full cycle? You figure out what that frequency or that bandwidth was. And 1 over that is time, because frequency is cycles per second. And so 1 over frequency is seconds. So that is where you get your number. You don't have to do that. But that is a way of you're looking at that. Now, one of the things is I'm showing you a trace that is on a linear scale, so it's a constant delay. When we get into the real world and we get some filtering going on, we're going to find that it's not a constant delay. It's changing by frequency. It's not just a bulk latency. And so it may not be as obvious as that, but that is a skill that you tend to develop after you look at a lot of these traces. So in this case, what we're looking at here is in both cases, we're looking at lead. So the measurement signal is leading the reference signal. Again, we're going to Vegas. So the thing I want to point out here is the top one, I'm putting on a linear scale so you can see it's a constant amount of delay. Of course, as soon as you put it on a logarithmic scale, that's what it looks like. That's what a constant amount of delay looks like. The top is a half a millisecond of lead. The bottom is a full millisecond of lead. So what we're seeing is the steeper the slope is, steeper means more, and then the direction means lag or lead. So the way you're going to use this is that in this situation, say you're going to take the measurement, you're going to have two systems and you want to combine their energy. And so one of the first things we're going to want to do is time our systems, right? We want them both arriving at the same time. So I'm looking at this with green system and red system. I take these two measurements and I should take them with the same time reference. That's kind of important. But basically, I take my green measurement, my red measurement, which system's energy is arriving first? Well, if I walk myself through this, red is going up angle, so it's leading. Green is going up angle, it's leading. Who's leading more? Red is steeper, so red's leading more, so red is arriving first. So if I'm going to time red to green, unless I have a magic undelayinator and I can take delay out, what we're going to have to do is add signal delay to the red system to get it in time with the green system. It's a decision you make all the time when you're looking at phase traces on an analyzer. So this one right here, this is a classic situation. What we're looking at here is we're looking at a green system and blue system. So at this frequency right here, what we see is they're both showing lag. So who's arriving first? Well, in this case, blue is less steep, so it's less lag. So blue is arriving before green, which has a steeper trace, so more lag, so he's arriving later. So what we're seeing right here at 160 is a situation where the relative phase between them, now we go over here and we compare numbers. Right here, those systems are in phase, but they're out of time with each other. That's one of those situations. There are some old dog tricks you might run into. A classic one is I got to set the timing for my sub to main. That's going to be a subject of I think not this Friday, but next Friday. Don't know which one, but that's the classic question. I need to time my subs to my mains. That's because while most of us don't have to do a crossover between mids and highs in our main system, we normally rely on the manufacturer for that. The one crossover we do have to time quite often is timing mains to the subs. And so you say the old dog way of doing that is to go, okay, first figure out where your crossover is. So, measure your low system, measure your high system, figure out where they're equal level, and then look at that point, flop the polarity of the sub and play with the timing until you get the biggest null there, because that's the equal level point, right? So when I get them to be 180 out from each other by adding or subtracting delay there I know they're 180 out. Then I reverse the polarity of the sub again, and I've got addition through crossover. It doesn't mean you're in time. all it means is you're in phase. I could be a cycle out, I could be 2 cycles out, but it is a nice thing that you're at least getting addition through crossover at that one position. Anyway, this is a situation where we've got the 2 systems are in phase but out of time. In this situation, we've got the same slope at the same frequency. So these systems are in time. Same slope at same frequency means same timing. However, they're in phase, they're 180 apart from each other. We're going to take a look at this later, but this is an indication that they're in time but out of polarity. And then this last piece right here, we've got our 2 systems, and here we've got in time and in phase. So in general, when you want to get stuff in time and in phase, you're just looking to overlay the phase traces over each other. And so it's a pretty simple, straightforward thing. It's just saying in this region, these 2 systems are in time, in phase with each other. We should get good addition. Okay, so what I'm going to do here is I'm going to jump over and I want to take a look at some basic measurements, and I just want to reinforce some of this. Now, this is something I would suggest that you do at home. Can you pull up the diagram of our system for a second, the SOFO system? So what we're looking at in the system, the points that I'm grabbing to do this measurement is I'm just grabbing the input of the DSP and the output of the DSP. So those 2 positions right there are the 2 signals that I'm comparing. That's what you're seeing on the screen. So let's jump back over to the screen. And that's what you're seeing right here. The pink up top is the output of the console, and the orange is the output of the DSP. So I'm going to jump over to the transfer function. Okay, so in this case, what I'll do is I'll zero out my delay in my measurement, right? So now my delay is zeroed out. I ask you a question, have we set our delay? Well, there are 4 places on this screen that are saying no. There is the live IR, and if the delay was set properly, this impulse would be dead center. There is the magnitude response. The coherence is saying, nope, you got something messed up here. If I look at the number over here, it says 0, so I haven't set my delay yet. Pretty obvious. The reason why I saved this one for last, though, is now that we can kind of read the phase trace, it's going down angle, right? If we figured out it's going, here's 250, here's 500 cycles, 250 to 500 cycles, that's 250 cycles to go 360. So that's 4 milliseconds if you do the math. You don't have to, because what's really cool is we just hit our tracker, boom, and nail it. And we find that our delay time was 4 milliseconds, right? So now we can see he's in time. What I'm going to do here now is I'm going to type in, and I will go, hey, let's move my delay time to 5 milliseconds, right? So I'll go ahead and capture that, and I'm going to call this 1 ms lead. What this means is, what we can see here is this is the 1 millisecond of offset that we were just taking a look at. When I get to 250 cycles, we're at 90 degrees. When I get to 333, let's see, 333, we're right there at 120 degrees. Pretty cool. We get to 500 cycles, we're at 180. So this was the data we just took a look at. So that's kind of cool. So one of the things I want to do here is, in the upper window, I'd like to get a better view of what's going on up there. So what I'm going to do is I'm going to click in that window. Now I've just told Smaart, hey, I'm talking to you. And then what I'm going to do is I could zoom in here. I could drag a zoom like that. But we also have preset zoom. So what I'm going to do is I'm going to come over here and go Command, Zoom, Zoom number 1. And so I'm zoomed in to plus or minus 10 milliseconds. So we see right here that this guy is leading. So here's the center of the screen is my reference signal. So he's leading by a millisecond. Okay, so what I'm going to do now is I'm going to become an interior designer, and you'll understand in just a second. So instead of 5 milliseconds, I'll type in 3 milliseconds for my delay time. Ooh, pretty. So what we have here now is, instead of previously we were showing lead, now we're showing lag. Now, here's a really kind of cool thing here is remember I told you this is a continuous plot. So let's say I'm interested in what's going on around 500 cycles. Well, he's going off the screen and then he continues on the bottom, but let's roll that to the center of the screen. So now, so basically the phase trace is just a circle, so I can roll that so that I don't have to have 0 in the center. I can have 180 in the center or 230 or whatever in the center. So I can roll that around and get a good idea of what's going on there. And if I want to put 0 back in the center, I just click on the boundary of the plot. It goes back to default. All good. This is why I would say don't click on the boundary of the upper plot for what we're going to be doing in this and next week or next session. Don't accidentally click on this guy right here. He'll take you back to default and you'll have to go to Command Zoom number 1 or Option 1 was what the hotkey that was showing me. Okay, so now I've got a situation where I've got 1 millisecond of lag. What I'm going to do here is I'm going to hide that other trace. Now, what we've just done is we're just taking the two traces and we're moving. I have a system with 4 milliseconds of delay. So I set my delay. Too much delay, not enough delay. So now I'm in the situation where not enough delay. So I'm going to come over here and in my measurement engine, there's a plus and minus right underneath the delay, and that's going to allow me to add in delay a sample at a time. The way that we do our delay is just by register shifting. Basically, our delay is in samples, and so right now we're running at a 48K sample rate, so 48,000 samples per second. So one sample is about 20 microseconds, and so you'll notice that as I increment this, as I add delay, you notice that it's going in increments of 0.02. What's really cool though is you see that in the top window, because this window up here, this window here, and this window down here are the same information. This is the time domain view of the response of the system. This is the frequency domain view of the system. This is saying that he is lagging by something less than a millisecond. So is this. They're both saying the same thing. And so I'll come in here and as I bring them into time with each other, you can see the phase trace flattening out. Oops, I went too far. I go ahead and knock it back, brought it back into time. You might see me in later episodes, and I might have done it in the last session as well, is sometimes when you take your measurement and you use the tracker or whatever to set your delay time, you may find that your phase trace might be angling up or angling down, and you want to flatten that out. You can just change your time reference. You're changing the time reference. The phase response is still the phase response. You're just changing what you're referencing to in time. Okay, so that was kind of cool though. That was, if any of you, I'm going to make something up. If any of you have ever done azimuth adjust for tape heads, so a lot of people watching this, unfortunately, never had the pleasure of aligning tape heads. But basically, you might know that process from the XY on a O-scope. It's just you're just trying to get that phase trace flat, and so that just tells you they're in time. A flat phase trace says everybody's in time, everybody's arriving together. So the next thing I'm going to do, what we've been doing is we've been moving the reference signal around. So we have the measurement signal fixed, and I'm moving the reference signal around forwards and backwards. So the next thing we're going to do is I'm going to take the delay time, and I'm going to take that delay time and I'm going to set my measurement delay to 10 milliseconds. So effectively what I've done is I've gone and put my reference signal out. My reference signal is now stuck out here at 10 milliseconds. My measurement signal now is leading by some amount. But what I'm going to do here is I'm going to come over and I'm going to change the delay through the system. And so what I want to do is I want to adjust the system till the output of the system is arriving at 10 milliseconds. Now, when would I do something silly like this? I would do this all the time. Let's say I'm setting a delay for a system. I have my main system, I measure that, I set my measurement delay to the arrival of the main, then I turn off the main system, I turn on the delay system, and I adjust its delay of the system until You can see him coming into the center. Woo! Bringing him in, bringing him in, bringing him in, bringing him in. Boom. There we go. And so I nailed it. So if I came over here and I hit find, measure the delay through the system, you notice that the delay time I come up with is 10 milliseconds, of course, because that's what the phase response is saying. And so in this case, there I was timing one system, making sure the output of the system was arriving at 10 milliseconds right there. Okay, so I'm just about to do a little bit of game. We play this in the operator fundamentals when we do this. Everybody's set up in their computer. To play this game, you can't have the live IR showing. So I'm going to hide the live IR. The other thing is you can't hit find and you can't hit track. That's too simple. It's cheating. And so what I'm going to do is I'm going to take this guy and I'm going to type in some delay into this system. Okay, so I'm going to use the phase trace to find the latency through the system. So what is this saying? Well, the phase trace is saying I'm lagging. My energy is lagging. I'm not arriving at, right now I'm set to 10 milliseconds. It's sometime later. So to do this, all I'm going to do is I'm going to guess at the delay time until I can get this time nailed down. So it's a game of playing hot and cold. So I'll start with, I don't know, 20 milliseconds. All right, I'm still lagging. So I'll go to 30 milliseconds. Got closer, but still down angle. I'll go to 40 milliseconds. Oh, I went over. So now what I'm going to do is I'm going to go, I guess, 35. So 35 is close. Now I'm going to use, what is happening here? I wonder if I'm going to crash right in front of you. So I'm going to do this just by guessing. So I'll do 37 milliseconds. I'll do 38. This is interesting. I would hate for this to crash. So let's see if I can trim this down now. There we go. Boom! I found the delay through the system. Now, let's see what happens if I hit find. I had 37.90. It comes up with 37.90. Yep. So I found that. If I turn on the live IR, there we go. So I found the delay. I've just found the delay through the system. Okay. So that is reading that slope of the phase trace to find the timing in the system. And so remember, it's just lagging, on time, leading. And so we're at a point where I think that we're about as far as we want to go with this session. So I'm assuming there are some questions. No questions? Do we know?
Yeah, there's some good discussion. We have learned that the YouTube chat is not performing to its fullest extent right now. But if you want to maybe clarify again the difference in where you're choosing to take your reference signal pickoff and how that influences the relative timing of everything else you're going to take.
Okay, so what I'll jump over into my PowerPoint over here. I'll go back to that slide where we're talking about time zero. So here, what I'm doing is I've grabbed the output of the console that's sitting over here. So that's what's feeding the DSP. So that's sort of my time zero. Then I grab the output of the DSP, that's my other signal. And basically through this guy right here, that DSP unit, there's 4 milliseconds of delay through that unit. When we first measured it, there were 4 milliseconds of delay through that unit. And so what I had done was that I quickly had measured it and set 4 milliseconds of delay, and so I had basically delayed this signal to this one. So that's what we did right here, right? So I put the signal in, so I grabbed it at time 0, I measured the delay, I applied that delay, and so they were in time with each other. So effectively, this is one of those cool things about the transfer function. The transfer function allows you to isolate a system so that and this is one of the kind of important things about being aware of what your system is, because if I grab my signal before it goes into the mixer, if there's any latency through the mixer, that's going to be in my measurement. So a lot of times I want to be downstream of the mixer, and I just want to know about the time through the system and the time through air. And so the thing is that we did, the last time we did our measurement, when we did room EQ resultant, right? When we were doing room EQ resultant, what we did was I grabbed this point to this point, so I was measuring the EQ. I grabbed the output of the EQ to the microphone, so I was measuring this room in the speaker, and then I was measuring them both together. And what you might have seen was that the delay that was the propagation from this point to that point, from my mix out to my microphone, equaled the delay in this system plus the delay in that system. And then one of the things that we notice about the response of this entire system is the response of this system plus the response of that system. The cool thing about it was we were able to isolate the DSP and measure that even while we're measuring the system. So we're measuring two things at the same time, apart from each other and then together. Now this was more of an issue. I mean, when SIM first developed this process for that analyzer, it was done specifically because it was using analog EQs, analog parametric EQs, and so you really didn't know exactly what it's doing. I think one of the cool things that's happening now is that, of course, with the digital equalizers, they know exactly what the equalizer is doing, and so they can show you what the curve of what it's doing, unless they don't want to and want to draw you a curve that's only suggestive of that, and we can leave that aside. But basically, you don't have to measure your DSP now normally, although that's the whole thing. Does their graph of what the EQ is doing actually match what it's actually doing? Well, that's why you have an analyzer. So you can go in there, this analyzer is as much for, hey, what does this box do? What's going on through here? What's, is it net inverting? What's the latency through this device? This is one of the things that this tool is there for, is just for checking your gear. One of the things that you might do on a tour is from time to time go through your mixer. I mean, that's the great and horrible thing about mixers, not the mix engineer, but the actual console, is that now they have so much capability and layers of capability. And so it's probably a good idea to go through and measure through your console from time to time to verify that nothing weird is going on in there. And I'm not sure how you define weird and what I define weird, but generally what you're going to do is you might take this signal and you'll loop it back in, so your measurement loop is in to out. And then what you can do is you can change where you're getting your ins and your outs to try and include and exclude certain things in your chain. This is also going to become important when we start talking about hooking up our smart rig to our system, is where we're grabbing this signal. One of the things that's happening quite a lot, I like to have the DSP, the alignment DSP, the system control DSP to be downstream of the mixer. So the mix is creating the art that's going through the system, and then this alignment DSP is all about just trying to make the system accurately reproduce that signal. So the thing is that oftentimes now you start to get consoles that actually have the output DSP inside the console. Well, now if I grab the output of the console, compared it to the microphone, effectively what I've just done is the output of the console is actually at this DSP out. So I'm getting a measurement of the system without the EQ included in your loop. And that can be that can be dangerous because you could have EQ inserted in and you're blind to its effects. So one of the things that you're going to want to do necessarily is find a way to get a pre-DSP, pre-system DSP point to grab as your reference signal. And, you know, like I said, there's so many things that can happen in here. One of the worst things in the world is to have, like, in your measurement, on your measurement signals, to have EQ or compression inserted in those channels, because that's just going to throw you off in your measurement. But that's the way of the world now. The cool thing is that there are often relatively easy ways of grabbing the signal in the console before it goes through the DSP, beyond the pale of what we're talking about right here. But I'm sure that any number of people could jump in and discuss that offline. As I've copped to before, I am not a mixer. I hang out with them. I sit next to them, but I am a terrible mixer. So I'm probably not the person to ask about it anyways, but there are a host of people available that can answer that question. So any other questions?
No, I don't think so. I think that pretty much covers everything for today.
Sweet. We nailed it down an hour. That was the more straightforward stuff. Just remember, lagging, on time, leading. Let's see. Oh, yeah. Left to right, downward, lagging energy, horizontal. Now it doesn't have to be horizontal slope at 0 degrees. It has nothing to do with the degrees on the side of the plot. You just need to go, when you go from downward slope to upward slope, that inflection point is the 0 point. That's what you're timed to in your measurement. What's going up is arriving early, down. So that's one of the keys to reading a phase trace. The bigger headache is then as you get into the question, why? Why does it work like that? Why does a filter cause phase shift? Some of these questions we'll touch on. Some of them we're not going to have answers for you in these sessions. We have a couple of different sources where you can go and read. There's a lot of good instructors out there that have a deep background in the knowledge on how DSP filtering works and things like that. So we can hopefully point you in a direction to get some of that information. But next session, what we're going to do is we're going to start filtering and looking at some interesting phase responses and maybe start looking at timing some stuff together. So thank you very much.